Hello, students. Today is a lesson by interchangeability, standardization, and technical measurements. Theme 1. Basic concepts of terms and definitions of interchangeability. Plan of our lecture you can see in our slide. 1.1 Types of interchangeability. 1.2 Interchangeability and dimensional accuracy. 1.3 Roles of predominant numbers. 1.4 Nominal valid limit sizes. So we can start. Item 1.1 Types of interchangeability. Modern production of machinery and equipment, their exploitation and repair are based on the use of the principle of interchangeability of parts, assembled units, and aggregates. Interchangeability, the property of independently manufactured parts to take their place in the assembly unit without additional processing during assembly. At the same time, normal work of products is provided. The principle of interchangeability. The principle of interchangeability, a set of scientific and technical provisions, the implementation of which in the design, manufacture, and operation ensures the interchangeability of parts, components, and products. Interchangeability is not provided only by the accuracy of geometric parameters. For example, the gears are made to the specific dimensions, but some of them do not provide the required hardness of the teeth during thermal hardening. The resulting gears have a shorter service life, and the interchangeability of the assembled components will be violated. The modern direction of interchangeability is functional interchangeability. Accuracy and other exploitation indicators of parts, assemblies, and products must be agreed with the purpose and operating conditions of the final product. Interchangeability in geometric parameters is a private type of functional interchangeability. So, one more time, interchangeability in geometric parameters is a private type of functional interchangeability. Interchangeability is complete and incomplete, external and internal. Full or complete interchangeability allows to receive the set indicators of quality without additional operations in the course of assembly. There are also cases of group selection of parts, selective assembly, the use of compensators, adjusting the position of individual parts of machines, fitting, and other additional technological actions when assembling machines. Such interchangeability is called incomplete. It can be carried out not on all, but only on some parameters. External and internal interchangeability. External interchangeability is the interchangeability of components and components in terms of exploitation parameters and connections dimensions. Internal interchangeability is ensured by the accuracy of the parameters required for the assembly of parts into assemblies and assemblies into mechanisms. And now we start item 1.2, interchangeability and dimensional accuracy. Interchangeability of products is ensured by the accuracy of their parameters in practical size. However, in the manufacturing process, errors inevitably occur, the numerical values of which are found by the formula. Delta x suffix I is equal x suffix I minus x, where in this formula x is the specified size value and x suffix I is the actual value of the same size or parameter. Errors are divided into systematic, random, and gross. First type of errors is systematic errors. Systematic errors are errors that are constant in magnitude and direction, or that change according to a certain law. They can be caused by errors in the adjustment of machines, wear of cutting tool, etc. The influence of these errors can be considered and even eliminated. Next type of errors is random errors. Next type is random errors. Random errors are errors the magnitude and direction of which cannot be predicted in advance. Their appearance is due to approximately the same influence of a large number of independent random factors. Random errors can be caused by instability of chemical, physical, and mechanical properties of materials, variability of the sizes of preparations, change of force of cutting, errors of measurements, etc. And the last type of errors is gross errors. Gross errors are errors that clearly do not correspond to the processing or measurement process. They are not taken into account. In the conditions of mass production, the distribution of random errors that occur during the processing of parts is well described by the law of normal Gaussian distribution. In practice, interchangeability is ensured by limiting errors. And one more time, in practice, interchangeability is ensured by limiting errors. Now we start item 1.3, rows of predominant numbers. What is predominant numbers? Predominant numbers form series of numbers built on certain laws. The most appropriate are the series built on arithmetic or geometric progressions. More often apply the series constructed on geometrical progressions. Word experience has shown that the requirements of all industrial must fully meet the series of predominant numbers that make up geometric progressions with denominators. Q is equal x root by 10. Where in this formula x is the exponent of 5, 10, 20, 40, or 80. There are 4 main and 1 additional series of predominant numbers. The degree of the root x is included in the symbols of the series. The 5th row R5, the 10th R10, etc. The series of the best numbers are endless. They can be extrapolated to both smaller and larger numbers. The series of predominant numbers served as the basis for the standardization of linear dimensions. There are 4 main series of nominal linear dimensions denoting R5, R10, R20, R40. ISO recommendations establish the predominant numbers and series of predominant numbers, which are the decimal series of geometric progression with denominators. For R5, U is equal 5th root by 10 is equal 1.6. For R10, Q is equal 10th root by 10 is equal 1.25. For R12, Q is equal 20th root by 10 is equal 1.12. And for R12, its last row, R12, Q is equal 40th root by 10 and is equal 1.06. R80 series with denominator 1.03 is also allowed. The basic preferred series of the best numbers. For R5, Q is equal 1.6. You can see the row R5. First item 1.0, second item 1.6, then 2.5, 4.0, and 6.3. For next row, it's R10. U is equal 1.25. First item, R10. First item, 1.0. Second item, 1.25, because Q is equal 1.25. And next item, 1.6, 2.0, 2.5, etc. And next row, R12. Q is equal 1.12. R20. First item 1.0, second item 1.12, and then 1.25, 1.4, 1.6, 1.8, 2.0. And the last one for R12, 20, 40, not 20. R40. Q is equal 1.06 and R40. First item 1.0, next item 1.06, then 1.12, 1.18, 80, and 1.25. Construction on basic preferred series of normal sizes on the basis of series of the best numbers allows to provide coordination of the sizes of products with their other parameters: power, productivity, speed of rotation, etc. The system of normal linear dimensions does not apply to derivative dimensions that depend on the accepted initial dimensions and parameters, included technological interoperational dimensions. And now we start item 1.4, nominal, actual, and limit sizes. The inner cylindrical surfaces are conventionally called holes and denote big D. The outer surfaces are conventionally called shaft and denote small d. One more time, for holes we use big D dimensions, and for shafts always use small d. Dimensions express the numerical values of linear quantities and are divided into nominal, real, valid, and limit. Dimensions express the numerical values of linear quantities and they divided into nominal, real, and limit. Nominal size or basic size is the size for which the limit sizes are determined and the deviations are calculated. Nominal dimensions are the basic dimensions of parts or their joints. They are appointed as a result of calculation of details on durability, hardness, wear, resistance, and on other criteria of operability. Actual size. D suffix R, big D for holes and small d for shafts. The size, actual size, the size set by the measurement with the allowable error. And limit dimensions are the two maximum permissible dimensions between which the actual size must be or may be. The larger of the two limit sizes is called the largest limit size, D suffix maximum, and the smaller limit size, D suffix minimum. Big D we use for hole, small d we use for shaft. To simplify the drawings, limit deviations from the nominal size are introduced, which are placed next to this size with the sign plus or minus. The upper limit deviations, big ES and small ES. Big ES for holes, small ES for shafts, is the algebraic difference between the largest limit and nominal dimensions. And lower limit deviations, big EE and small EE, big EE for holes, small EE for shafts, is the algebraic difference between the smallest limit and nominal dimensions. For the holes, we use the formula big ES is equal D suffix maximum minus D, or big EE is equal, and big EE is equal big D suffix minimum minus big D. For the shaft, small ES is equal D small d suffix maximum minus D, and small EE is equal D suffix minimum minus D. The real deviation is the algebraic difference between the actual and nominal dimensions. And on this slide, you can see questions for current control of the type 1. Use it for preparing for the next lesson.